Now we're going to get into actually finding some limits without having to look at a graph. And I've mentioned that in some cases the limit is just the y value. When it's a nice smooth function, there's no holes or jumps or anything like that, you can actually just plug the a value, what you're taking a limit to, into the function and get your limit. And when we're able to do that, that's called direct substitution. So we're going to talk a little bit in this video about some things that we can just use direct substitution to find the limit. So we don't have to do anything fancy. We don't have to look at the calculator or look at the graph. We can just plug the value into the function. So one group of functions that's always allowed are polynomials. Okay, so things like x squared, x cubed, and we're adding them and multiplying them by numbers. And so what we can say, this theorem says that if p of x is a polynomial, then for any real number a, we can say that the limit as x goes to a of p of x is equal to p of a, meaning the limit, you're just going to plug the a value, what x is going toward, into your polynomial. And it's as simple as that. Okay, so the only reason I have this calculator here is to actually do the plugging in, nothing crazy. So here it says find the limit as x goes to 5 of x squared plus 3x plus 2. Well, I'm just going to plug 5 in for x. So we'd have 5 squared plus 3 times 5 plus 2. We can do that in our calculator. 5 squared, 3 times 5 plus 2. Okay, and our limit is 42. And that would just be the y value of the polynomial at 5. Okay, the next one says the limit as x goes to -1 of x cubed minus 5. Same thing, that's a polynomial, so we're just going to plug -1 in. So -1 cubed is equal to -1 minus 5. So our limit here is -6. Okay, we've got one more polynomial. We want to find the limit as x goes to 3 of x to the 4th minus 3x squared minus 2. So we would do 3 to the 4th minus 3 times 3 squared minus, that should be a 2. 2. Okay, so use the calculator. 3 to the 4th minus 3 times 3 squared minus 2. So our limit here is 52. Okay, so whenever you have a polynomial and you're trying to take a limit, it's a very easy process. You're really just evaluating the polynomial at that a value. Okay, now rational functions are just functions that you have a polynomial divided by another polynomial. So they look like a fraction, but just the top and the bottom are both polynomials. Now, as long as the a value that you're going to is in the domain, and another way of saying that is that it's defined, which for a rational function, all that means is that a does not make the denominator equal to 0. So as long as it doesn't turn the denominator into 0, you can use direct substitution. So mathematically we can say the limit as x goes to a of r of x is equal to r of a. So anytime you have a rational function, you can plug it in and not get 0 in the denominator. You can just use direct substitution to find the limit. So we've got two examples here. We've got the limit as x goes to 7 of x cubed minus 5x plus 2 over x minus 3. And we'll put this in the calculator, so we're going to want the numerator and the denominator in parentheses. So we're going to have 7 cubed minus 5 times 7 plus 2 over 7 minus 3. So I'll put this in the calculator just like that. So parentheses 7 cubed minus 5 times 7 plus 2. Close the parentheses, divided by 7 minus 3. Okay, so here we get 77.5. In calculus, we generally like to put things back in fraction form, so we can hit math, and say turn it into a fraction. So enter, enter, and we see as a fraction form we get 155 over 2 as our limit. Okay, and we had one more. So here we've got the limit as x goes to 2 of x squared minus 16 over x minus 4. So 2 doesn't make the denominator 0, so we'll plug it in. 2 squared minus 16 over 2 minus 4. We can put that into the calculator. We get 6, so our limit there is 6. So, kind of the main point of this video is that for polynomials, you can always use direct substitution. And for for rational functions, as long as the denominator does not equal 0, you can use direct substitution.